This is consistent with what we said the first week, right? So I just want to remind you, but now I have a location for you, so we'll be in BAC. Is this BAC or is this the other one? Yeah, right across the way, BAC 316. That's where we'll meet, 7 p.m. on Tuesday, December 10th. Possibly. It's the same building. I don't know if it's the same room. It's going to be one of those huge rooms like that, yeah. Nope, it's all my 270 and 171 students. So it's going to be 3 classes altogether. Okay, other questions? Are we good on the final exam? Okay.
How long do we have for the final exam?
It's technically 2 hours, but we'll probably stay longer. So as long as every year the custodians basically kick us out. So I try to give as much time as we can. Okay, so I want to have a little conversation here. So this is what we've been doing. We've been inferring about functions using derivatives. So recently, almost every question I've gotten has demonstrated a faulty attempt to memorize a rule and a disregard for meaning and reasoning. So this is this swirling pit that would just are like attracted to like a magnet. Okay. Oh, if this is true, if it's this, then this. All these rules. Okay. And like I said, the questions have demonstrated that you tried to memorize a rule and you didn't memorize it right, and so then because of that, you can't get it. Okay, so don't throw away all the stuff that we're working on in class relative to this stuff. Don't throw away all the meanings and understanding in exchange for memorizing rules. Okay? This is what happens. You try to memorize a bunch of rules and you forget the rules and then you have nothing. Okay? You have nothing. You have nothing. Okay? So if our original function is f, what does that mean? What are we talking about? What is that? Okay, this side's got it. What does that mean? What is the original function? What is it about? Accumulation. And is the input or the output? X values or Y values? The actual quantity that's accumulating? The output, the Y values, right? That's accumulating as some other quantity X changes. Okay? So that's our accumulation or amount. Okay? So what about the first derivative? Right. So we said it's the rate of change of the accumulation with respect to changes in this other quantity X, this baseline quantity. So we have this baseline quantity X changing. It might be time, it might be volume in the bottle or something like this. And then we're focusing on this output quantity that changes as X changes. And so the first derivative is the rate of change of that accumulation with respect to X. And then the second derivative, the derivative of the first derivative. What will the meaning of that be? She said the rate at which the rate of change is changing. With respect to?
X.
With respect to X. Okay, it's the rate of change of R with respect to X. So don't try to find rules for yourself that you're bound to get confused about and not memorize correctly. Always, whenever you're doing problems, always try to attach meaning to what's going on. So if the value of f, the function, is 0, what does it mean? The value of f is 0. Does it mean we have a max or a min? No. See, they're trying to memorize a rule, not even considering what f is. What does it mean for f of x to be 0? What's that? Does it mean it stopped accumulating? Right. At that moment, the value of our amount is 0, right? It just means our value of our amount is 0. Okay? So that's an example of getting confused because you try to memorize something. So know what the functions mean, and then every question that's asked, and as you work through these problems, keep relating it back to these meanings of accumulation and rate of change. And so what is it? So why is it that we want the rate of change to be 0 to find maxes and minimums of the accumulation? What's the connection there?
The accumulation just stopped.
Right. So here he's saying the accumulation is increasing, and then what happens at the max? Yeah, the accumulation, it's not increasing anymore, it's not decreasing. So it pauses, and that represents the high point. Okay, or the accumulation is decreasing. And then it stops decreasing and starts to increase. So right for a moment there, the rate is 0, it pauses, and so that's why we get a low point. So keep relating everything that you're doing. Instead of trying to make the structure of rules for yourself, instead keep practicing your understanding, and then you don't need any rules because you can always reason through. Okay? So that's my great encouragement to you. This understanding what's going on and using meanings is going to take you far further and far greater than rules that you might end up with a good set of rules that works for the test, and then but next semester you're going to forget all the rules. Okay? Understanding stays with you. Understanding stays with you. Okay, so I want to do, at your request, I want to do one of these 4. That's not what I wanted. This. Is there one of these written problems that we should work through? Which B? 10B? Yeah, so is there one of these that was caused the most difficulty or would be worth talking about? Which? So nominations, 10B. Are there any other suggestions? We'll take a vote.
10B.
I heard 10A, I heard 10B. Any other suggestions besides 10A or B? Those were both. All right. So all in favor of 10A, raise your hand. All in favor of 10B. All the rest of you got them, no problem. So problems with both, so it doesn't matter. But okay, here's some more for B. So we'll do 10B. So 10B is it this picture right here? Okay, and so the rancher plans to make 4 identical adjacent rectangular pens against a barn, each with an area of 100 meters squared. What dimensions of each pen would minimize the amount of fence that must be used? So we've got a nice image of this. Sometimes you don't have an image, and that you want to be good at reading the given information and creating a representation, an image of what's going on. If it's asking for the dimension of each pen that minimize the amount of fence that must be used. What are we trying to minimize? Yeah, so we're trying to minimize the amount of fence. So if we just had one kind of centerpiece of this whole problem, what would the centerpiece of this problem be? If we're trying to minimize the total length of the fence. How do we, some of you have said it, but how is it that we minimize a quantity? How do we use calculus to minimize a quantity? Yeah?
When there is a graph of the total fence length function,
Okay.
it will be the minimum value.
Okay. And a graph is just a representation of a function, right? So if we're minimizing the total amount of fence, then the centerpiece is going to be the total fence length function. So area is involved because but it's really not a function. It's fixed. Okay. So area is involved, but really the centerpiece of this is a function that gives us the quantity of total fence length, and then minimizing that function. So looking at the graph isn't really using calculus to do that, right? So looking at the graph really using how do we use calculus then to minimize this function? So we're trying to minimize. How does using calculus? How can we use calculus to do that? Marco.
assuming write a function that would accurately depict like what you're trying to find in the picture. So you'd have to do lengths times with some of it. I'm not sure.
Okay, Steve.
Well, would you relate the area function and the total fence function and take the derivative and set it equal to 0?
Okay, so you talked about two functions. The derivative of what?
The derivative of the total fence function.
Right. So the derivative will help us find places of max and min.
But you need a point, like a value, so you can substitute it into the total fence function from the area function. Else it won't work.
Okay, so the area is simply going to help us build this function. The area's relationship is going to help us get this function. Okay, so it's not really an area function, right? The area is fixed. It's not an area function; it's fixed. Ryan, go ahead.
I don't know. I'm just throwing this out there. Do we need to sum up the total area that we're trying to create in order to relate that to the total fence length function to then? I don't know that.
Yeah. So we need a function. And then we want to try to find that this is going to be different configurations that could give us different lengths. And then we want to find which configuration will minimize this output. And so that's from taking the derivative, right? So, okay, so now let's take a look at this. What do you want to call x and y, Melody? So you're gonna say there's some lengths here. So what's x and what's y? But you labeled these as, you checked W and L, right? Didn't you label some distances here as W and L? That's what you were telling me. What's that? Sorry.
The way that I did it is that I just went kind of conceptually what I understood the area.
Okay. Yeah, so we're going to minimize the amount of fence and use calculus to do it. We need a fence length function, and we're going to use the first derivative to find that minimum value. Ross?
Well, since the total fence length function is in terms of the length and width.
Okay.
You start with the area, since it's length times width, but then you need to put it in.
But we need to define these we need to define, when you're saying length or width, we need to define them before we can do anything. So how are we going to define our length?
For length, I said it was the side of one of the rectangles, and then the width is the bottom of one rectangle.
So you called the length this right here?
Yes.
Okay. And you called the width this right here?
Well, either way. But like,
I'm not sure.
It works either way, but you did the opposite.
But if you call this length, then you're saying this is width?
Yes.
Okay.
And then you need to put, when using the area, you need to find one in terms of the other.
Okay, so you guys are really focused on area. It's important, we need it, but the focus is the length function. So let's build this length function, and then we use other things to help us get that length function the way we want. Okay, for minimizing the length of fence, then the centerpiece of the problem is a length of fence function. So what will this length, now that we've defined that this is W and this is L, what is our length of the fence? Somebody knew. What's that? 5W plus 4L. What do you think?
Well, that's.
What?
Is it 2W plus 4?
Okay, so I'm hearing 5W, I'm hearing 4W, and 2W.
Did you just do 100 divided by 90?
Yeah, so we're not to area yet. We're just trying to get this basic length function. Yes, we're getting there. We're getting there, but it's jumping ahead. So is it 5W, 4W, or 2W? There's 5 of them, right? 1, 2, 3, 4, 5. So 5W plus 4L. Now the question is, so there's a problem with this, and that's that we have this length function in terms of two quantities. We want it in terms of one. So take your pick. Which one do you want to make L a function of? Okay, I'm hearing W, so W is great. So if we truly want it L as a function of, capital L as a function of W, then what? Now we have to rewrite this in terms of W. So how do we rewrite L in terms of W? Yeah, now so now we see this relationship. That has to be 100. So LW is 100. What's that? Yeah, thank you. Okay, so L is? Okay, so do you see how this, that's the only place this area thing comes in to this whole process. Now we're done with that. So there's just this one little step where we use the area. But this whole problem is going to be about this function of total fence length. Okay? The area was just to help us get that in terms of one quantity W. So here's this the center. If we're minimizing a quantity, the centerpiece of the problem is the function of that quantity. Are we good? Does that make sense? Okay, so how are we going to minimize that quantity? We know that the first derivative, the rate of change, can help us pinpoint a possible location of a minimum. How does it do that? First derivative. Yeah, so if we get a pause, right? So if our function is at places where it pauses, our potentials for a minimum. And if it pauses, the rate of change is 0, right? The rate of change is 0 if our accumulation pauses for a moment. So now this is the easy stuff. And so we want a pause in the accumulation. So what are we doing with the derivative? Set it to 0. Is it the square root of 80? Okay, and so because we don't talk about lengths of fence in terms of square root, we'll do that later. So then it says what dimensions? All right, so this gives us the minimum amount of fence. Is it right? What's that? Okay, so we could find the value of L, and that would give us the minimum amount of fence.
Oh, no, you need the second derivative.
Why the second derivative, Ross?
Because you need to figure out if you need to find if the square root of 80 is a max or a min.
Yeah, so all we found was that all we found by this was that when W is square root of 80, we have a pause. That's all we know. So we have to verify that it's not a max or something different, but that it truly is a min. So how can we verify that this W value is truly a min of L? Yeah, Peter. Oh, sorry. Peter, go ahead.
You take the second derivative of the L function.
Okay.
So that would be negative 400 W to negative 3. Or no, not negative 400, negative positive 800 W to negative 3.
Okay. And then what?
Then you set that equal to 0.
We'll set that equal to 0. Agree with that? Yeah, we want to know the status of our second derivative at this point. That's what we want to know. We want to know what we've got. So we're going to plug square root of 80 in. And is it going to, so all we need to know is it positive, negative, or 0. So 800 over positive number cubed. Don't even have to calculate it. We know that is positive. So what does that tell us about this length function if the second derivative is positive?
It's a minimum.
And why does it tell us it's a minimum?
Because the tangent line is always increasing, or the rate of change of the first derivative is increasing throughout.
The rate of change, not of the first derivative.
Yeah.
Right. The rate of change of our length function is increasing, right? So a positive derivative means the thing you took the derivative of is increasing. So that means the rate is increasing. An increasing rate means less negative, more positive, right? So looking at the slopes, the inclination of the curve is becoming less negative and more positive. Therefore, a first derivative of 0 with a second derivative positive means minimum, because you've got a pause with an increasing rate. An increasing rate and a pause makes a minimum. So we're good. So we got a minimum, and so now L is going to be 100 over that. And so once we get exact values for each quantity, then it's good to say, all right, let's get a decent decimal approximation, because you're not going to specify to your builder that you want something the square root of 80 long, right? So what is the square root of 80? Someone crank it out. 8.9 something? 8.94 meters. And the corresponding length would be 100 over that square root of 80. 11.18 meters. Okay, any questions? So do you see how this was 95% about the length of the fence, that function, and about 5% about area? You see that? Area was just a vehicle to get this length function in one variable. That's all the area was.
So that's the dimension for the total tank, not each man.
So it goes back to how we define W and L. So this is a value of W. So what did we say W was? What did we define it as? Which dimension is it? This is a value of W. So if you know exactly what the quantity W represents, then you know what that number means. So what does the quantity W represent? So it's the distance, it's how deep from the barn it is, right? So it's this dimension right here. And then length is 11.18. So what is the 11.18 meters? Is that the whole pen? Yeah, so if you want that dimension, that's the whole pen, what will you do? Multiply 11 4, and you get that whole dimension of that, the whole length from all the way from the left to the right. Other questions? Okay, so let's work on some more. Okay, so for the rest of them, you're going to keep them, and you can redo them, keep going on them, and they'll be part of Friday's homework, okay? So you keep it, and if it's good the way you like it, you can just turn it in with Friday's homework, but now you have time to revise it, or change it, or do what you didn't do, okay? All right, so let's do more here. Okay, so here's a problem. An A-frame barn is to be built that's 30 feet high, 40 feet wide, and 60 feet long. A rectangular room is to be built inside the barn so that its ceiling abuts the roof. What dimensions should the room have so the volume is as large as possible? Okay, so do you know what an A-frame structure is like? It's all roof. It's all roof, okay? The walls are the roof also. It's like the shape of an A. So you're going to make a rectangular room inside so that the ceiling abuts the roof. So sometimes you're given a situation and you don't have the image. And so that's going to be first. Can you represent the situation with a good image? So take a minute and see if you can figure out, make an image of this. Yep, the A-frame barn is 30 feet high from the apex to the ground, and at the ground it's 40 feet wide. So see if you can make an image of this. What's that? It is three-dimensional. But there's an asterisk on that. There's an asterisk on that. What? Don't let that intimidate you. Don't let that intimidate you, is what I mean. Yes, sir? So it's up against. So we're trying to get the maximum volume of a room possible. So we're going to make that ceiling as high as we can. So it's going to be, does that make sense? It's remains right. Remains rectangular. Yeah. So basically, instead of maybe this is better. The height of the rectangular room is limited by the roof. How about that? The height of the rectangular room is limited by the roof. Okay, so what about the fact that this is three-dimensional? Why does that not intimidate us? What's that? In terms of drawing a picture. Yeah, so do you have to draw a three-dimensional picture is what I'm asking. You don't have to. Okay, the length is 60 feet long. It's just a constant. And it doesn't really change anything. So you can just do a two-dimensional picture. Okay, so I see some good pictures. So is this what you have? Okay, so what are we trying to do and what will be the centerpiece of our solving process here? What are we trying to do, so what will be the centerpiece of our solving process? Something about volume. So, Shannon, what will be our centerpiece function in this problem? What quantity will be the output of our centerpiece function? Okay, and what is that? What quantity is that? I'm not asking for the formula, I'm just asking for what quantity are we focused on? Volume, okay? So the whole point of this problem is going to revolve around a volume function. And so in general, that formula will be for this particular volume. Yeah, so it's going to be length times width times height. So the question is, what one quantity is going to be our independent or input quantity here? So we want to be wise about that. So really what happens, so what is changeable here? So how can we change the situation to get different volumes? you change the width, then what happens to the height?
It has to shrink.
Yeah, so if you increase the width, then the height has to shrink, right? If you make the width narrower, then the height increases. So somewhere through here, there's going to be a room with the maximum volume. So what are we going to call our x? What do you want to call x to make life as easy as possible? There's different choices. So you said something with width. So do you want to make x this whole dimension here? Is there another choice related to width that we could use? Might be a little better. So how are we gonna, so can you foresee how are we gonna get then write the height in terms of the width? Where's that, how is that gonna, how are we gonna get that? What's that?
Instead of using the whole width of
Okay.
the rectangle, you just use half where it meets the height of the triangle.
And then why would that be helpful?
Because then height of the rectangle becomes like it's just subtraction from the height of the triangle.
Okay.
Choose length.
What's that?
Choose length. Isn't you see those constant?
Yeah, but so then we only get, if we use x as a constant value, then we only get one volume. Yeah, so it's got to be something that changes, right? It's got to be, our input variable has to be something that changes for which we get different volumes. Okay, so looking down the road, it will be, what Ross said is going to be helpful, and we're going to see in a second. So using that as an x dimension is going to be helpful. Half of the width, right? Half of the width. Okay, so
the width of the entire rectangle.
Yep, but I'm trying to get you to see down the road that there's a reason why this is going to be an easier choice. Okay, in terms of finding what that height is. Finding that height in terms of this quantity is going to be a little more straightforward than in terms of this quantity. Okay, does that make sense? All right, so what is our length? So we're writing our volume function then. What's our length?
60 feet.
60. What's our width? It's x. Is it x? 2x. Okay, and then the question is, what's our height? So we need, what do we need? We need that height in terms of that quantity x. How are we going to do it? Any ideas? So the area of the rectangle. The area of the rectangle would be height times width. But that's changing, right? So that area is basically just like the volume, and it's changing as x changes. So how are we going to get
We use Pythagorean theorem.
Pythagorean theorem? Okay, how about that? Is that, so are you looking, what triangle are you looking at?
Half of the overall A. So like you have the center line drawn down the middle of that big triangle.
Yeah.
Use one of those halves as for Pythagorean theorem.
Are you looking at this big triangle here?
Half of that.
Half of that.
Oh no, like, yeah, what you just outlined, yes.
This one?
Yes.
Does that have the height dimension in it?
No, but we can find it.
But it's proportional to the smaller page.
Yeah, so Pythagorean theorem isn't going to be a good route here. But some of you are mentioning a different approach here. Which would be what? There's proportionality here, and someone said similar triangles. Okay? This is going to be the most helpful way to work with this. So see if you can do it. See if we're trying to get h in terms of x. And we've got some similar triangle relationships that can help us do that. So take a minute, see if you can do it. Can you get h in terms of x? H is this one right here. So remember, you got some dimensions here. Don't forget, this is 40. And this is 30. Any success? Kevin, any success? Do you see what we're trying to do?
I know what's going on.
So we're trying to relate, we're getting a relationship of h of x, and we're going to use similar triangles to do that. So what triangles are similar here that we can use that? Sterling, any ideas?
The top triangle with that has the as its base is similar to the whole triangle.
By the whole triangle, do you mean this one?
No. From A to B to C, or A to B to break up.
Well, wouldn't it be,
Yeah, but from A, this whole triangle doesn't involve the quantity h, so
well, couldn't you do like,
we want triangles that involve h and x. That's what we want to focus on to get h and x related. Yeah, Kevin?
well, couldn't you do like half of 40 is 20, so
Okay.
the side length of 1 would be like 20 minus x.
You're looking over here?
Yeah. Well, the whole, like from A to where it says width, that's 20.
Right.
That's 20, so like just the x part, that'd be 20 minus x,
Right.
which would be where like the A to the dot is.
So 20 minus x is from here to here.
Yeah. And so you already have the length of the total is 30.
The height?
Could you do, then you use, you said don't use Pythagorean theorem, right? Because couldn't you do like 20 minus x times the h? That's what your is.
No, we're trying to relate h and x. We're trying to relate h and x. We want h in terms of x. So that for x here, we can put an expression of x's into this right here.
Oh, okay, so
Anything wrong? Yeah, did you get it?
Yes.
Tell me.
Is 30 over 20.
30 over,
20.
okay? So you're looking at this 30 right here over
Over 20.
over 20
And equal to
equal to
h over
h, right?
yes. Yes. H over 20 minus x.
So he's saying this big triangle here is similar to this little one way to the left here. And so that ratio of the height of the little one to its base is the same as the ratio of the height of the big one to its base. Okay, so now can we solve for h? And we got h in terms of x.
so it would be 20 h equals 30 times 20 minus x. Or that.
And so you said it's 30 minus, what is that, 30 minus 3 halves x? Does it make sense? What's that? Is there?
No.
You're good?
Yeah.
Okay, doesn't make sense. Could you have done it yourself? That's the key. So could you have, so this is a lot slicker or a lot more efficient than Pythagorean theorem, which would be a mess. Okay, but sometimes Pythagorean theorem is the way to go, but these similar triangles make for a very nice, easy formula. Okay, so we got equals 60 times 2x times we're going to stop here. Let's talk, though, through what we would do from here. What would we do from here? We're trying, what's our goal? So, again, centerpiece of the problem is a volume function because we're trying to find maximum volume. So tell the person next to you, what will the rest of the process look like? Go.
value where
Yeah,
right
this
on.
is and this is
Maybe that percent.
well, no, it's a derivative of this set to zero. So
No, I guess what I'm saying is
oh,
zero equals whatever,
yeah,
whatever implies.
yes.
You just want to find the natural
That shows us that how time is great.
So like when the rate's zero,
So what if it's not?
just need the most positive we're looking for, right?
Well, no,
It's like max, you gotta find the maximum.
Okay, any questions?
Hey, good graph.
So these setups of the functions is really that's the most challenging part, and they're all different. Every single problem is different, and it's about understanding the quantities in the situation, modeling them well, and getting that function. From there, maximum or minimum means where the derivative is zero, or where that accumulation function pauses, and then verifying that you have the type of optimum that you want, either a max or a min. Okay, so like I said, you can continue working on those problems that were due today, and then I've added some more. This next round, they're harder, okay? So trying to improve their ability to solve. See you on Friday.
Explains.